Okay, now it's recorded.
No,
There
I
we
can
go.
see.
Okay, cool. Okay, so hello everyone. Welcome to the first workshop of the semester. As we mentioned, today we are exploring variable selection algorithms for causal inference. As the name suggests, these are computational methods which help researchers tackle one of the fundamental challenges in causal analysis, determining which variables actually matter when trying to understand cause and effect relationships. Specifically, today we're going to be looking at double lassos, aka double least absolute shrinkage and selection operations. But before diving into the specifics of lassos and double lassos, I should explain what we mean by causal inference, why as social scientists we care about establishing causality, and why careful variable selection is crucial when attempting to identify causal relationships. So as social scientists, we are fundamentally interested in understanding cause and effect relationships in society. You can say that causality is the center of all science, essentially, right? We're trying to understand um, usually the effect of one variable on another, especially in quantitative work. And so we make causal claims all the time in sociology and social science, education. We argue these higher income, social media affects political polarization, childhood poverty impacts life outcomes, but actually proving that these relationships are causal, improving and demonstrating the actual impact, how impactful each cause is very challenging, especially in the social sciences when you're primarily working with observational data, right? In an ideal world, we could do what, I guess a lot of medical scientists do and run experiments, double blind, random experiments, randomly assign people to different education levels, different childhood conditions, different social environments. But in social science, this is rarely possible or ethical. Maybe one day with AI, we can create fake people or something. But for now, we are stuck with our observational data. Um, and we can't randomly assign people to poverty or wealth or assign to get to college. So what do we do instead, right? We try and establish causality in other ways, right? And so, one of the primary ways that people think through causal inference and causality is what we call the potential outcomes framework. In this framework, causal inference compares what actually happened to what would have happened under different circumstances. For instance, the effect of education on salary. Ideally, we'd want to know how much someone earns with a college degree compared to how much that exact same person would have earned without one, right? So we have our treatment variable, education, we have our outcome, salary. We want to know what is the effect of education on future earnings. Of course, the major challenge here is that it is impossible to observe both scenarios in a real life setting. Let's say we're looking at person A who went to college. We can see their current salary, but we can never know exactly what they would have earned if they hadn't gone to college, all other things being held equal. This is called the fundamental problem of causal inference. So what do? We try to approximate the missing information using other people in a data set. We might find person B who didn't go to college and compare their salary to person A's. But for this to be valid, we need person A and person B to be as similar as possible in every other way that might affect their salary. Whoops. This is where confounders come in. These are variables that relate to both our cause and our take parents' SES for socioeconomic status, for example. Right? Parents' SES affects both the likelihood of going to college and future earning potential. So when you compare person A and person B, we want to make sure their parents had similar SES levels. By controlling for these confounding variables, we can get closer to estimating the true causal effect of education on salary. However, um, when we're dealing with modern data sets and trying to understand causal relationships, we often run into issues where we have high dimensionality in data sets. By this, we mean that there are a ton of variables. So for instance, you look at ad health, there's 2,799 total variables in ad health rate of one. You know, if you're not familiar with ad health, which, probably everyone here is, it's big UNC, CPC, um, health database where it follows adolescence into adulthood. collects data such as friendship networks, family relationships, health behaviors, education outcomes, neighborhood characteristics, genetic markers, etc. You know, and when you're trying to study a particular cause and effect relationship in ad health, so like one of these variables of interest, how do you know of all of the other potential variables, which ones are actually going to be relevant to your study? And then also, and sorry, I have to move around my screen stuff. In some data sets, the number of possible controls is going to exceed the number of observations. That is not true of ad health, from what I understand. I think there's like 20,000 people in wave one, 799 total variables, but still a lot of variables per observation. And so, even with ad health's substantial sample size, dealing with this many variables presents significant challenges. With again, with 2,800 variables, how do we decide which ones matter for our specific causal questions? Which ones are the crucial confounders we need to control for? Traditional approaches to variable selection become unwieldy to scale. And so because we can't reasonably include all variables in our analysis, not only would that be computationally intensive, but it could also lead to noise, a roaming, or signal. But we also don't want to leave out important variables because that could bias our results. So this brings us to the central question. When we're faced with thousands of potential control variables, like in ad health, how do we systematically determine which ones actually matter? Which variables do we actually need to include to get an accurate estimate of our causal effect? And this is where double lasso regression comes in. Statistical method that helps us tackle exactly this problem, variable selection in complex data sets. Jen, I think you wanted to mention something on this slide.
Yeah, so before we get into the details of what the lasso actually is, I did want to call out a couple great resources for UNC students. So I actually took an ODM course on this a few years ago. I think it's offered in the fall. It's Introduction to Statistical Machine Learning using R. Highly recommend it. They go over techniques such as this, but also some others. And then there's actually an upcoming ODM course, which is Advanced Statistical Machine Learning, which happens online. It's April 24th. I'm signed up for it. Highly recommend. I think you have to put down a deposit of $35, but then as long as you attend, I think over 2/3 of the course, you get a full refund on that $35. So if this type of stuff interests you, I do highly recommend signing up for that ODM course.
Great. Thank you, Jenna. So let's get into the last. Oh, whoops. I think it read my thumbs up there. All right, something in the chat. Quick. Um, okay, I'll read that later, Scott, but it seems interesting. Um, yeah, so let's just start with just understanding machine learning a little bit, specifically supervised machine learning. So what is machine learning, right? Machine learning is essentially training a computer algorithm to do analyses by recognizing patterns in a training data set and then taking the patterns that it recognizes in the training data set and then trying to see how well it does on a testing data set that it is unfamiliar with. In supervised machine learning, we're trying to teach computers to recognize patterns by showing them examples where we know the answer or we think we know the answer. Think of it like teaching a student and give them practice problems along with the correct answers, hoping they'll learn the underlying rules and patterns. And in machine learning, we want to make sure our computer student has truly learned these patterns and they're not just memorizing specific examples. And that's why we typically split our data into different portions, some for training or teaching our model, and some for testing how well it performs on new examples it has not seen before. So this brings us to a crucial challenge, overfitting. We have a lot of variables in our model. Like in ad health, it's 2,800 variables. We risk creating a model that looks great on our training data, but fails on new data. Uh, we might get excellent predictions and high R-squared values on our training data, but poor performance on the testing data. And this is where lasso, or at least absolute shrinkage and selection operator, comes in. It is specifically designed to help us avoid this overfitting problem by reducing model complexity and identifying which variables are truly useful versus which ones might just be noise in our data. So let's understand why adding more variables to our model can be both helpful and problematic. This brings us to what we call the bias variance trade-off, which is fundamental to understanding why we need methods like lasso. When we add more variables to our model, we generally reduce what we call bias. That is, we get closer to estimating the true relationship on average. Think about the ad health data. If we include more relevant control variables, we might get closer to understanding the true causal relationship we're interested in. But there's a catch. As we add more variables, we increase variance. Our estimates become more unstable across different samples. Imagine if we ran our analysis on different subsets of ad health data. With too many variables, we might get wildly different results each time. The model becomes very sensitive to the specific data that we're using. They're dealing with a trade-off. Include too few variables, and we risk missing important relationships, high bias. Include too many, and our estimates become unstable, high variance. This is why we need sophisticated methods to help us find the right balance. And this graph here visually illustrates the trade-off we just discussed, right? On the x-axis, we have model complexity, which increases as we add more variables. And on the y-axis, we have prediction error. Look at the blue line. It shows how our model performs on the training data. As we add more complexity, the error keeps decreasing. The model appears to be doing better and better at fitting our training data. But the red testing line tells a different story. Initially, as we add complexity, our testing error decreases. We're capturing real patterns in the data. But then there's this turning point. Here you see, after a certain level of complexity, our testing error starts to increase again. This is overfitting. The model is starting to fit noise in the training data rather than real patterns that generalize. In the sweet spot, the optimal level of complexity is where the testing error is at minimum. This is what we're trying to achieve, a model that's complex enough to capture real relationships, but not so complex that it fits noise. Lasso helps us find this balance automatically through adding an additional tuning parameter in our normal regression model, which Jenna will now explain in more detail.
Cool. Yeah. So before we get into the tuning parameters specifically, I did just want to take a second to look at some of the equations underlying the bias variance trade-off. So if we look at the total model error term, which is the top line here, we can actually see that it's broken down into three different component parts. So the first one is going to be that bias squared, which, as Jacob mentioned, the bias is the difference between the estimated parameters and the true underlying parameters. So we can see that in the very first term of this equation, where we see f hat of x. And so that is our estimated parameter value minus the actual underlying parameter value, which is just f of x. And then the second term there is going to be the variance. So once again, as Jacob mentioned, the variance is how much our estimates of the parameters actually differ across training data sets. So we see that we have our actual for this current training data set, we have our estimated parameter value denoted by f hat of x, and then we subtract the expected value f hat of x, which is like the average or expected value of the estimated parameters across all of our different training samples. So once again, the variance captures, how different our parameter estimates are going to be according to the different training data sets that we have. And then, of course, we have an irreducible error term that is just kind of impossible to access with our models. So on the next slide, we can see this trade-off visually, right, where we have bias and variance that are both contributing to the total error. And so our goal is to somehow find the model parameters that are going to minimize the total error. And that is our optimal model complexity that we're aiming to tap into with the lasso. So with that lead up, what is the lasso? Okay, so I think one of the most helpful ways to understand the lasso is in direct contrast to least squares regression. So basically, least squares regression minimizes the sum of squared errors. So what least squares does is takes the actual values of y minus the fitted values of y and squares that error and finds the minimum value there. And what the lasso does is it actually adds some type of penalty to this error term. And so in doing so, it actually shrinks the regression coefficients. And this is called regularization or penalization. And so basically, by minimizing this new function that includes the least squares plus lambda and the sum of coefficients, we're minimizing the least squares such that the sum of the absolute values of the coefficients stays below a certain constraint. And so kind of what this works out to is requiring that the combination of parameters stays below a certain value. So for example, on the left-hand side here, we can see that if our S is equal to 100, then we're constraining our estimated parameter values such that they have to add up to 100. In the example here, we're constraining our parameter values to be 75 and 25. But one thing that, that demonstration there leaves out is this lambda term. And so this lambda term is actually our non-negative tuning parameter, which dictates how much of a penalty we're actually applying to our estimated coefficients. And so in this way, it's actually able to control the model complexity. I do want to call out here that if we look at the equation and we set lambda equal to 0, it actually just becomes our least squares estimation procedure. But typically, lambda will not be 0, and we will be imposing some type of penalty in order to achieve that optimal model parameterization. So now on the right-hand side of the screen here, what we see is what it actually looks like and what it means when lambda takes on different values. So here, what we're essentially doing in this lasso is setting lambda times the sum of all of the coefficients to be less than or equal to some threshold. So in the second line on the right-hand side, we can see that when lambda equals 1, we get the same coefficients. Oh, I think I switched them there. It should be 75 plus 25. We see the same coefficients that we had on the right-hand side without any lambda value included. If we increase our lambda value to 25, our coefficients have to shrink in order to still fit the threshold that we set. So they reduce to 3 and 1. And if we really increase our lambda value to 99, our coefficients become really, really small. They become 0.75 and 0.25. And that's once again to keep the coefficients below this threshold that we're imposing. And so what we can see is that as we increase our tuning parameter, the coefficients for the least associated variables end up being reduced. And over time, and not over time, eventually, some of them will become 0 when lambda is big enough. It's important to call out that when lambda is super big, so when it heads to infinity, all of the parameters will be 0. So the important thing about the lasso is that actually in between 0 and really, really large values of lambda, there are still some coefficients that are reduced to 0. And so what this allows us to do is to find the control values that are actually important for our model. So one way of looking at this is geometrically, which I found very interesting. So basically what we can see on the left-hand side here is our error surface that least squares tries to find the minimum of, right? So it tries to minimize that mean squared error. And so when the error surface is projected onto the coefficient plane, which is where we have our B1 and B2 as our X and Y axes, we take the middle of that circle as the OLS solution, right? So that is the point that minimizes that kind of 3D parabola that we're seeing on the left-hand side of the screen. But then what the lasso does is it actually imposes an additional constraint on those parameter values. So on the next screen, what we can see is that the lasso requires that our estimated coefficients fall somewhere within that square. And so that square is the geometric image of having lambda times the parameters less than or equal to a given value. And so what happens is because it's a square and because in higher dimensions, the shape will have different corners. The corners fall along an axis. And when the solution is along one of the axes, the parameters that are 0 on that axis will be 0 in the model. So in this instance, the estimated parameter values are at that top corner of the box where it touches the ellipses coming out of the OLS solution. And at that point, beta 2 is actually 0. So in that instance, beta 2 is 0. And so we're actually removing some of the control variables from the model. Okay, so as you might recall, I mentioned that lambda is actually estimated. So what happens is as we are using the lasso, We iterate across different values of lambda, and this is where the machine learning that Jacob talked through earlier actually comes in. So what happens is lambdas go through what's called k-fold cross-validation. So our entire data set is divided into however many folds that we decide. In this instance here, we can see that there are 5 folds. So there are 5 different subsets of our data. And we go through 5 different iterations of this process for each value of lambda. So what we do in the first iteration is we take the first 4 folds of our data and we estimate a model based on those first 4 folds. And then we apply the model to the test set and see what the error is. How different are our predictions from the actual Y values in the data? And we do that across each of the different folds of the data set such that each fold becomes a test set. And we take the average of those errors, and that becomes our mean squared error for that lambda value. And so what we can see on the next slide is that we actually do this across a bunch of different lambda values. So what we're trying to do is we're trying to find the lambda that has the lowest mean square error. And so this will iterate multiple times, which Jacob will go through in the code later. And then we'll select the lambda that has the lowest mean square error value. And that's the lambda or the penalty that we apply in our lasso. So that's really where the machine learning element comes in here. So as a summary, overall, the goal of the lasso is to prevent overfitting. So what we're doing is we're actually inducing bias into the parameters. So we're making them not quite as exact as we possibly could, but we're trying to reduce the variance of the parameters across different training data sets. And so throughout this process, the least related parameters will end up being 0. And we did want to call out that you can run into issues if multicollinearity is too high. So if certain potential control variables are highly related to each other, the lasso is usually only going to select one of these highly correlated predictors and drop the rest. But you actually don't know which one will be selected. So what you can do to try to diagnose if this is happening is see if you get different non-zero parameters each time, and that might indicate that something is happening with multicollinearity. And then overall with the lasso, you can run it over many values of lambda to then find the optimal value of lambda to ensure that your mean squared error is the lowest. Okay, why don't we maybe pause there? Does anyone have any questions on single lasso? All right, cool. Great. So that's the single lasso. But of course, we
Can I?
are going through, yes, go ahead.
Yeah, sorry. I just wanted to jump in to say 2 things real quick. One is something to be aware of with any type of lasso estimation or regularization estimation is that because you're introducing bias into your coefficients, they actually aren't interpretable anymore. So lasso regression is a common strategy for different, regression estimation beyond just the case of variable selection, especially in high dimensional models, because it just helps you reduce complexity and eliminate noise. But whenever you're using a lasso estimator or another regularizer like a ridge estimator or something, you actually can't interpret the coefficients. And so the most common way to do it is to do a standardized coefficient so you can determine the rank of the coefficients in terms of relative size, or to do something like a G estimation where you're using predicted values, because an implication of the bias variance trade-off is that your coefficients actually are biased in terms of their interpretation, but your predictions are more accurate than they would be otherwise. And so by transforming the effect interpretation to the prediction space, you can get a better insight. The second thing I'll say is that lasso estimation does suffer from extremely strong collinearity, but it's actually robust to strong collinearity as compared to the OLS estimator in terms of variance. And so if you have issues related to collinearity, lasso and ridge regression can actually be a solution sometimes, even though if it's too high, it can cause those estimators to underperform. So I'll turn it back over to you, Jenna and Jacob.
Cool. Okay, thank you. So today we are actually going to be expanding upon the lasso to talk about the double lasso. So one of the things that perhaps was floating in the back of your mind as we were talking through this is, if we're interested in something like the effect of education on income, what if, according to our lasso, it actually tells us the coefficient on education is 0, right? So when there's a certain variable that we really want to test the relationship of that variable with our outcome variable, how can we make sure that we keep that variable in our final model such that it doesn't actually get reduced to 0 in this process? So the answer is we do 2 lassos instead of just one. So the first lasso that we do is,
Jenna, are you sharing screen?
no, Jacob is.
I don't see a screen. Do other people see a screen?
I see a screen.
Okay, it's a me problem.
I see it.
Okay, cool. So what we do is we actually do 2 lassos. So the first thing that we do is we actually take our treatment variable, or here it's the cause variable, and we do a lasso on all of the potential controls in our model. And then we do a second lasso of the effect variable on all of the potential controls in our model. And then from these 2 lassos, we take the union of the variables that, is the union right? Or is it the other one? Anyway, we take all the variables that are related to either of them and put them in a regression. So we can see this with our example of level of education on income. So if we have, all of those 8 possible control variables at the top, and we're trying to figure out which controls we should actually include in our model, what we first do is we do a lasso of level of education on the controls. And so in this example here, we find that, parental SES, race, and genetic markers are related to level of education. And then we do an additional lasso of income on the control variables. And in this example here, we find that parental SES is also related. But then we also find that private versus public school is related. So then what we do is, after we complete those 2 lassos, we take all 5 of those control variables that the lassos found, and we do one final regression of those 5, including those 5 variables as controls, and also including the level of education as our key predictor of income. So that's kind of like the overall logic of what we're going for here with the double lasso. Any questions on that?
Hi, Jenna, I have a question. So,
Yes.
for the first lasso, you can, like lasso can only identify parental SES, race, genetic markers, but not the private versus public school, right?
Yep.
Okay, so for the second lasso, identify private versus public school, and then you like combine like all of them, right?
Exactly.
Okay.
Exactly. Yeah, Fernando.
I just tried to think, and also maybe it's just because of the shape of the model, but if it's in both, would you be able then to say that it's either the parental SES acts as a moderator and or mediator of the relationship between level of education and income?
That's a great question. My sense, because I was also thinking about this, Scott, correct me if I'm wrong, but my sense is that this method is intended to identify the direct effect of level of education on income. So we're not actually bringing in any assumptions about mediation or moderation. This is really just to remove any other association with any, kind of third variable in this sense. Scott, anything to add there? I can't see him. No. Okay, he's shaking his head now. Great. All right, cool. So before we get into the code on this, I did want to take a second to talk through a recent example in PNAS. And so what we can see is that the author here was trying to look at the effect of racial segregation on COVID-19 mortality. And so this is actually why I was thinking about, whether it's a direct effect or mediated effect, because I thought this example was certainly one where some of the control variables could potentially be interpreted as mediators, but really what we're trying to look at here is the direct effect. And so our goal is to figure out what are the best variables to control for confounding when we are trying to look at the direct effect of racial segregation on COVID-19 mortality. And so if we go to the next slide, what we can see is the outcome of two different lasso regressions. So the one on the left-hand side looks at the associations between county attributes, so all our potential control variables, and COVID-19 mortality, so our outcome variables. And then on the right-hand side is the association between our main predictor, so that relative diversity index, which is how we're operationalizing segregation, and all of our possible control variables. And so through the lasso, the author ended up with 18 controls that were included in the final model. So we can see here that, just from looking at this, we can probably guess at what some of those controls were. So we can see that percent Black is highly significant in both models. So we can imagine that that is likely one of the controls. If you're interested, you definitely look at the article to take a look at what controls ended up in the final model. But what they did was they ran OLS fixed effects and double lasso regressions to figure out how the relationship between the key independent variable and dependent variable changed under those different scenarios. So on the next slide, we can see the main results. So what they did was they ran an OLS regression with no controls. So it was just the main independent variable segregation regressed on COVID-19 mortality. So we can see that the coefficient here was about 0.36. And then they added in fixed effects for state fixed effects. You can see a bit of a reduction in that coefficient. And then with the double lasso regression, we can see that our coefficient has reduced quite a bit. And we find that the overall mortality rate is about 8% higher and infection rate is about 5% higher per one standard deviation difference in racial segregation. So basically, we can see that as we add more controls, we are accounting for some of the kind of original OLS relationship between the independent variable and the dependent variable. Right.
All right. Okay. My turn to take over again. Cool, cool. All right. Thanks for explaining the nuts and bolts there, Jenna. And now we will be looking at a demonstration in R. Can everyone see my screen? Yeah. Okay. Cool, cool. So this is a demonstration. We'll do a demonstration of a single lasso in R, and then we'll do a demonstration of a double lasso. So as Jen and I were exploring this, we couldn't really find, or at least there is no like R package for doing a double lasso. There's one that is published on GitHub but is not uploaded to CRAN yet. So we just kind of did one manually by just doing two lassos and then combining the results into a regression. And so, yeah, I just wanted to put that out there that, maybe this package will be published on CRAN soon. We included a link to the package, but it might make things simpler. But here we just did it manually with two lassos, as you'll see.
Maybe I'll send this so we can follow along.
Yes. What would be the easiest way to send it to everyone?
Could you just
I mean,
upload the R script to the chat?
Good question. Let me see. I guessing yes.
Jacob, if you want to start walking through it, I can. Oh,
All right, I
that
think I sent it. I sent the R Markdown file. Yeah, so if you're not familiar with R Markdown, if you are first year and you're in TED Stats class, probably going to be learning about R Markdown this semester. It's basically a way to organize R into these nice chunks that you can look at each individual section of your code, the results, the output. Makes things a bit tidier. Although I know people are moving toward Quarto now. Has anyone heard about this? Quarto, Scott, Justin? You haven't heard about it? Okay, like in the new R for data science book, they're like nobody uses R Markdown anymore. We're all using Quarto. Uh, and apparently it's like an outside function that is similar to R Markdown, but it lets you operate with multiple programming languages at once. Seems pretty interesting. So uh, yes, you can install packages directly from GitHub. For our purposes, we were just like, we'll just do it manually and then see. And I think it worked. Should have worked. But all right, so let's get started here. Part one, single asset. So this first chunk here is just, loading the necessary libraries. So we have glmnet, which is the lasso package. Data sets, which I think is already in R, but just making sure that it's there. This gives us some example data sets to work with. We're going to be using MT cars, which is, I think, like a 1980s database of like 36 models of cars on various um, variables such as like miles per gallon, horsepower, etc. Now we're using tidyverse for data wrangling and visualization. You don't need to. I guess you can do it in base R if you're like Scott, but we will be using tidyverse here. Cool. And so then this second chunk, so let's look at the MT cars data real quick. So here, you can see I'm not a car person. I don't really know much about, especially 80s cars. I mean, I recognize like Mazda. I don't know what a Valiant is. It has bad gas mileage. That's the only thing I can tell from this. But you can see some of the variables here. This is not a high dimensionality data set. Jen and I were trying to find a good example of a high dimensionality data set, but then we got really worried about data wrangling and cleaning and wanted to keep things relatively simple for our purposes. So normally, again, you're using lasso, double lasso when you have a lot of variables. For both examples today, we'll be using a lower variable data set. But so there's cars. You see, we got 30 something, 32 models of cars here. And let's say that we're interested in what aspects of um, these cars, so like how many cylinders they have, what their horsepower is, how that affects their fuel efficiency, so miles per gallon. So we are going to set first the non-miles per gallon variables as our predictor variables. We're going to set the miles per gallon as the response. And then we are going to standardize our predictors. So for lasso, you have to do this because it's going to be very sensitive to differences in variable scales. And the scale function just transforms each variable so that its mean equals 0 and its standard deviation equals 1. And then chunk 3 here. Sorry, lost my section in my notes. Chunk 3 here, we are just fitting the lasso model. So, oh gosh, my phone is freaking out on me. But we're fitting the regression model. My phone keeps closing the notes that I'm using. But here we use glmnet to fit the model to identify the most important predictors of miles per gallon. And this plot is going to show the lasso path, right? So as the regularization penalty, actually I should. So here you can see we have the coefficients values here on the y-axis. The x-axis is the L1 norm. So this is the regularization penalty. As the regularization penalty decreases, so it actually decreases from left to right. So as it weakens, more predictors enter the model with non-zero coefficients, but the steeper lines are the most important predictors that enter early. So we're going to be paying, most or not paying most attention to, but likely the most important predictors are going to be the ones that we see entering first here. So whatever this light blue line, this black line, and this light green line. here is because with the highest penalty, those are the ones that are appearing as important. All the other coefficients here you can see are 0 for the most part until we get into weaker regularization. And then here comes the machine learning part. Again, like Janet was explaining, we use cross-validation to figure out the best lambda. So first we got to set a seed for reproducibility here. And what this is going to be doing is going through and separating the data into chunks. I think this is a 10-fold set as a basis. So basically it's going to separate it into 10 different sections. And then it is going to, oh, see you, Scott. It's going to separate it into 10 different sections and then, train it on one section, or on 9 of the sections, test it on one section, and then it's going to do that 10 times. And the seed just makes it so that we're using the same divisions each time that we run this. And this cross-validation is going to help us select the optimal regularization strength. Right? And this plot shows the prediction error for different lambda values. The best lambda is going to be the one with the lowest error. So that's one that balances model simplicity and prediction accuracy. So you can see the log of lambda. The left line here is the optimal one. The right line, I think, is if you want a more conservative model that is going to have less coefficients, you would use the right line, the right dotted line. But the left dotted line is technically the most efficient or best lambda value, the one that minimizes prediction error the most. And you can see here what it is, 0.8007036. And then we can fit the final lasso model with this best lambda that we found. So we save the best lambda value, fit it to this model, we can extract coefficients here. And then I visualize the coefficient magnitudes for the selected variables. So here we can see what variables were actually selected. So in the end, only 3 of the variables actually mattered: the number of cylinders that a car has, the horsepower that it has, and the weight that it has. I did a variable importance visualization, but I'm not sure based on what Scott says whether this actually is accurate or not. So we will skip over the variable importance visualization.
From what I understood there, like which one, as long as it's bigger, is more important, but it's just you can't compare their numbers or their ratio. It's just their magnitude
okay.
does matter and ordering them. That's what I understood from what he said.
Okay. Then maybe this isn't all right. But then we can do a prediction. So, you'd ideally do this with different data set, but let's just predict our original data set that we have predicted values for the first 5 cars here. Mazda predicts 22 miles per gallon, Mazda RX-4, 21 miles per gallon, blah, 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 etc. Check right here. It's pretty close, right? 21, 21, 23, 22, 22, 21, 25, 20, 17. But it's getting ballpark. Any questions on the first lesson? Cool. I'll move into the double lesson. So again, we're just loading the libraries here. Just reload GLMNet just in case. We're loading this library called Matchit, which is where we're going to be getting our example data set here. And this library fast dummies is so that we can create dummy variables more easily, which we're going to have to do because we're going to have some vector variables here. And so the data set we're going to be using is the Lalande data set, which I originally thought was a French data set, but I think it's just the guy who made it has a French last name. But basically, it is this data set from, I think, the early 1980s, maybe the early 1980s, that looks at wait, sorry, I lost my description here. But basically, it looks at the effect of a job training program on income, controlling for a few different variables. So if we look at Lalonde here, you can see the treatment variable here is the job training program, whether they did it 1 or 0, age of the person, education, married, whether they have a degree or not. So I think this is years of education. This is whether they have a college degree. Their income in 1974, their income in 1975, and then their income in 1978 is the income we're interested in. Originally, the Lalonde data, before I transformed it here. Oh, it is a 1986 study. Okay, I just found my section. Has just a race variable, which has values of Black, Hispanic, and white. You can't use that in a normal lasso. You have to turn them into these dummy variables. And so Black was the base race, like value here, and then it's race Hispanic, race white here. So let's see. Move on to second section. Oh, there's a summary right there. I forgot I did that. Didn't have to go to the data. All right. Also, we're going to check to see if there's any missing values in the data set. Lasso will not work. There are missing values. There's no missing values, but just in case, set that up. And now, again, we're going to define our treatment and outcome. So our treatment indicator here is the literal variable called treatment. It's the job training program. The outcome variable is their income in 1978. And then we also have to define which variables are continuous and binary, which is going to matter for when we're setting up the scaling later on. And then again, we have to standardize the variables here. So we have to standardize the continuous variables. Don't standardize the binary variables. It'd be bad. We create, I guess everything would be 0.5 and negative 0.5. And we prepare this covariance matrix that has standardized continuous variables and the binary variables. So again, we just need to ensure that all the continuous variables are on the same scale and then combine them with the binary variables into a single matrix for modeling. And then here we're going to use LASSA to identify which covariates are most predictive of the treatment assignment. So these variables will help us understand how individuals were selected into the treatment group. So which ones actually underwent the job training program. So here we're setting the seed again, setting up our lasso treatment. We're going to, it has to be a binomial family here. So before we didn't set this, but we had to set it as binomial because our outcome variable is binomial. And we're going to extract the best lambda value and combine a bunch of the steps from the single lasso into this chunk here. And then we're going to extract the selected variables, label the coefficients, and then create a nice visualization here, hopefully. So you can see of the 8 variables that we have, 1, 2, 3, 4, 5, 6, 7, 8, all of them mattered for treatment, age, education, income in 1975, 1974, race white, race Hispanic, married, no degree. And now we're going to do the same thing with the outcome variables. Again, we're going to do this cross validation here. We're going to be trying to determine the best possible lambda, extract the coefficients that matter, identify non-zero coefficients. Sometimes, at least the example that we saw that Jen and I were looking at earlier in the package, it doesn't set it actually to 0. It sets it to a very, very, very small number because sometimes when you're doing the lasso, instead of creating actual 0 values, some of your values are just going to be like infinitely tiny. And so sometimes you have to account for that. That was not the case here, so I just set it to 0. And then the variables that matter for our outcome of interest. So your income in 1978, you have age, education, income in 1975, 1974, race white, race Hispanic, and married. You know, these are 7 of the 8 variables. You know, again, usually this is for high dimensionality data sets where you are going to be, you know, eliminating hopefully the vast majority of the variables that you're interested in. we only have 8 variables here. Turns out all 8 of them actually matter. So that's going to be useful, at least for our purposes. I mean, you know, they the guy Lalande did not uh, collect any unnecessary data. Shout out Lalande. And then here is where we combine them, right? So we combine the covariates selected from the treatment and outcome models. These are going to be the most important variables for understanding treatment effects. In our case, that is all of them. So we combine all of them here. There just shows you all of them. And then we're going to fit the final regression model, right? So the final model is just going to be normal regression outcome with variables, summary here. And then we see your income in 1978 was significantly related to whether you attended the job program, your income in 1970, or your education level, your income in 1975, 1974, and maybe whether you're Hispanic. All right, that is the R demonstration. Any questions? Sorry again that it's not a high dimensionality data set. So it ends up just becoming a normal regression. This is a common data set for causal inference. If anyone's interested in like testing other causal inference techniques, Lalande is very commonly used. I learned from the literature. Unfortunately, in our case, it didn't eliminate any variables, but it's useful.
This is super cool. Have either of you ever used lasso or double lasso?
I haven't personally, besides this.
Have you used it, Justin?
No, I mean I've read papers that used it, and I've never actually had a great background in it because this is I would prefer to do experiments where you don't have to really worry about variable selection or confounding the treatment. Yeah, but super
You're, sk
cool.
you're skipping all the observational downfalls.
Yeah, I literally skip like in a happy hopping way
Yeah,
all
yeah.
issues, and I know how the data were collected, and it's beautiful. And that segues actually into Scott's leaving message, which was he wants all of us to consider submitting a research brief. So there's a cornucopia of data problems that we can help sift through collectively. And we can talk about how to, as opposed to skipping over problems, how to dive deep into the muck and dirty ourselves with less clean data sets than the lawn or experimental. He also wants to encourage us to our next meeting on February 21st, where Risa's presenting some of her dissertation work. Not to cut off things too early, but I didn't feel like a strong, like, mountains of questions vibes.
No, that was a great segue. Yeah. Oh, Will has a question.
Yeah, just one question. So
Sure.
let's say you go through this process and it were high dimensional data and you started with 5,000 variables and you got down to 8.
Great.
Is the next step to just do your normal regression with 8, or are there other testing procedures to see if just like to check that specification, or do you just go with it and say number good and leave it at that?
Yeah, I think that there were some sensitivity tests that I read about. I don't remember them specifically. I think one issue, and Jenna, you can correct me here, is that the way, so because um, it's reducing so many coefficients to 0, when you have high like multiclinearity between two variables, it just randomly selects one to become zero and then the other one to not be zero if both happen to matter. Um, and so if those variables are highly collinear. And so that might be an issue with variable selection, right, Jenna?
Yeah, so that was something that Scott had added on to as well, right? It was it does well in high collinearity situations, but not like super high collinearity situations. So that's something that it's worth, running multiple times to make sure the actual variables that are non-zero don't change on you. That's kind of one back of the envelope way of testing it. I would also direct you to the segregation and COVID-19 mortality paper, because they had some sensitivity tests in there. Will, do you want to add something else?
Yeah, just a totally different question.
Oh, okay.
So the other question was, do you know, is it specifically looking at like coefficients that it's um like doing this trimming by, or like, I guess what I'm thinking of is, suppose you have a question that had where you expect the effect size to be small but still important.
Mhm.
Would Lasso eliminate that, or would that still be retained?
It should theoretically be retained, I think.
I mean, this is why you're doing the double lasso, is when, if you're looking at the effect of residential segregation on mortality, you're like, okay, maybe it's a small effect. So what I'm going to do is, like, if I do just a regular lasso, it might actually get rid of the coefficient on residential segregation because that effect is so weak. So that's actually kind of why the double was developed, in order to make sure your coefficients of interest don't actually get reduced to zero. So that's kind of the purpose of doing the regression separately and then combining all the variables together, is to make sure you're still maintaining the signal of interest, but you're controlling for the other variables that are most highly related to your variables of interest. Does that make sense? Okay, cool.
I'm going
I
to
have
stop sharing my screen for 1 second just to send the file out, but I can reshare it if anyone has a specific question about the code. I'm going to find the file.
Justin, did you want to add something?
not add something. I just wanted to ask actually a question. Um, Double lasso, if you took the intersection as opposed to the union, could that be informative in like a discussion or a different area to systematically identify confounders?
So this is where I'm not entirely sure. I was trying
I'm sort
to
of like
look.
curious about like the legitimacy of this ideal type, and does it actually like, it sounds useful. I haven't really seen that though.
I know I was thinking about it, especially again with this segregation paper, just because that was kind of the key empirical example that we were looking at. And I was thinking about kind of why you took the intersection, meaning variables that are related to either the treatment or the outcome, rather than only those variables that are related to both. And my thinking was that if there's a strong enough signal with at least one of them, then it's probably going to be a strong confounder, right? Like, that was kind of how I was thinking about it. But I guess I didn't do enough digging to see whether people actually take the intersection as opposed to the union, and kind of what the difference would be there.
It would just be noisier, right?
Less, would it be, wouldn't it reduce the noise if it was, I guess depends how you're defining noise.
Like I'm thinking that if something predicts treatment likelihood but has no effect on anything else, then you're gonna have noise in the causal, like this, yeah, you're gonna have error in the likelihood of treatment. You're not gonna control for treatment, and vice versa for outcome that's unrelated to treatment. And I think that's the intersection might be, I'm not arguing that we should only use the intersection. I'm suggesting that the intersection might be theoretically interesting.
Yeah, I'll have to look into that more. And I think to your point, that probably relates to whether you're trying to eliminate like only pure confounders or if you care about actually identifying the direct effect.
Yeah, it's cool. I have no idea. This is not my method specialty.
Yeah.
My most important question is it awkward when you're in the same room and then one of you has a question and you have to look at the screen as opposed to each other? And like, is that social situation interesting in any way, or is it used to at this point?
We're conducting an experiment, so stay tuned for the results.
I think people should be allowed to go at this point. Is there anything else?